Okay, so this is chapter 2 of EE131, chapter 2. And chapter 2, we will be talking about roots, finding the roots of some functions, some transcendental, nonlinear, transcendental, and polynomial functions. So here in chapter 2, we will be discussing some methods, techniques, on how to find the roots of these complicated nonlinear transcendental and polynomial functions. And we will divide it into three groups. The first one is the first group, we call them the bracketing method or iterative bracketing method. And again, this will be divided into several methods, which we will be discussing later on. And the next part will be the non-bracketing methods. Then the last part will be some intended for specifically for polynomial functions. Techniques. So these are Briestow's and Grape's root squaring method. So we will try to discuss them in this chapter. So we will divide this lecture into different videos. So it will be a long chapter because there's so many methods that we will be discussing. So in part one of this lecture, this first video, we will be talking about the bracketing method and under bracketing method. So for bracketing method, so this is the first one. Let's just call it bracketing method. Methods. So these are several methods. So we have graphical method, we have incremental search method, then we will also talk about bisection, and lastly, the false position. The first that we should be discussing will be the graphical method. Before we go to the different methods, first we need to understand how to graph, how to plot a function, and determine from that what's the root of that function. So before, if you remember, when we want to determine the root of a function, what we do is if we have a function of x, we equate this one to 0. So when that function is equal to 0, what is the value of x? Whatever the value of x at f of x equals 0, this one, then this x here is called a root, or sometimes we call it the solution. It can be more than one, it can be several roots. It can also be not just real numbers, it can also be imaginary numbers or complex numbers. So we just need to equate that function to 0, then we solve for x, then that will be the root of that function. So when will the function be equal to 0? So if we try to graph, because this is graphical method, so if this is our function here, f of x. So this is f of x. So where will be the root of this function if we look at it graphically? So the function becomes 0 when it intersects with the x-axis. This is the x-axis. And this is the y-axis. So when the function intersects with the x-axis, then the value of f of x is equal to 0. Obviously, if you try to extend that one to the y-axis, then it's equal to 0. So therefore, this point, this is where we can find the root of the function. So if we draw it graphically, you can see it immediately that whenever the function intersects with the x-axis, then that intersection, that point, is a root. And sometimes we call this one a0. So if that point is a0, then therefore a is the root of the function. And if we try to observe the value of f of x, considering this is a, so remember this is a from here, so this is a. So if a is less than, or our x is less than a, somewhere here, what is the value of our function here? So let's call it x1, f of x1. So what will be the value of f of x1? So if we project to the y-axis, obviously it's on downward direction, so meaning it's under the x-axis. So that value should be a negative value, and it should be less than 0. Then if you take another point greater than a, you can call it x2. What will be f of x2? So based from the graph here, if you project it again, it's at the top or above the x-axis. So therefore, the value of the function should be greater than 0. So what can we observe from this? So when the function changes its sign, so from negative less than 0 to positive greater than 0, we said that there is a root between that interval. So there will always be at least one root between that interval, between x1 to x2. So this is very, very important for numerical methods when we are talking about bracketing methods, because we want to bracket the method, meaning we want to change the upper interval and the lower interval. The root should be within that interval. So in solving the root later on using different methods, first we must know where we start finding the root. So we should know that between x1 and x2 there's a root. Why? Because if the signs of the function is opposite, it can also be interchanged. It can be f of x1 is greater than 0 and f of x2 is less than 0, as long as the signs are opposite. Then meaning between them there's always at least one root. So if we multiply f of x1 times f of x2, if this is a negative or it's less than 0, so this is less than 0 or a negative, then automatically between x1 and x2 has at least one root. So that's where we will be starting. Then, so if we use graphical, it's not accurate, it's just an approximation. But you can make it more accurate by zooming in the graph, by taking smaller interval between x1 and x2. You bracket again, and until you get the actual or the closer, the approximation. The advantage of a graphical approach is You can do it manually, anywhere, anytime. If you have pen and paper, you can manually draw the graph and you can approximate the root of the function. But the disadvantage of this one is it takes more time because you need to take more points along the function. You need to plot them. And sometimes if there's your values for x are out of the interval where the root can be determined, then it's hard to find the root. So you need to have a wider value for the x values. Let's take an example. Let's try to solve the root of this function. A very simple function, so that we can compare if our solution is accurate or not. If f of x is equal to x cubed minus 0.3. So what will be the root of this function? And we want to determine the root between from 1 up to 3. From x equals 1 to x equals 3. So what's the root between x equals 1 to x equals 3? So we use graphical. So we need to graph this one. So how do we graph this one? We take points. So we take values for x and y. So how do we choose the values for x? Basically, we are doing it from 1 to 3. So we can start with 1. When x equals 1, what should be the value of y or f of x? Or this is f of x. Or what is f of 1? So f of 1 will be 1 cubed minus 0.3. So you can use your calculator. Then here, this is a basic calculator. It's a 911 model. So you can, instead of manually inputting your values, you can first write the equation x cubed minus 0.3. Then we can now include the values for x. So first, you click calc, then it will ask you what should be the value of x. So first is 1. So if x equals 1, so 1, then press equals. Then this should be the value of f of x. It's 7 over 10, or this is around 0.7. Then after that, we go to 2. So for 2, so press calc again, and press 2 equals, so 37 over 10, or 3.7. And observe the value for the value of f of x. Then at x equals 3, what will happen? Calc 3, then equals, the value is 8.7. So we did solve from 1 to 3, and we observe. What can we observe here? The signs for the f of x does not change. So what does it mean? What's the significance of this? The meaning of this is there's no root. There is no root between x equals 1 to x equals 3. So before you try to solve a problem, make sure there's a root between that interval. So you can just plug in f of 1, then plug in f of 3. If you multiply them, if it's less than 0, then there's a root between them. But if it's greater than 0, then there's no root. Don't bother solving it anymore because there's no root between that interval. So what we will do is to find another interval. So we can either increase the value or decrease the value for x. So we can just decrease the value. Instead of starting at 1, you can start at 0. So if we start at 0 now, so this will all change. Let's remove this and this one. Instead of 1, we start at 0. So if we start at 0, so what is f of 0? F of 0. So we use again our calculator here. Press calc. Then you input 0 equals. Then there's the answer. It's a negative 0.3. Then how about f of 3? What is f of 3? So calc again. 3. It's positive. So f of 3 is positive. It's 8.7. So what's the conclusion? The conclusion is if we multiply them, the answer is less than 0 or a negative value. So meaning there's a root between 0 and 3. So we check it, there's a root. So next, what we do next is we decrease the interval. Instead of going from 0 to 3, we divide it into different intervals. So let's use one interval. So 0 to 1. So what will be f of 1? So use again your calculator, f of 1. So calc 1. Enter. It's 0.7. So 0.7. So from this, you don't need to continue calculating 2 and 3 because we already did that and we found out that there's no root between 1 and 3. And we also found out that in 1, it's now positive. So it's positive. It's 0.7. So this means that there's a root between 0 and 1. So the root of this function is lying between x equals 0 and x equals 1. So what we do next again is to decrease the number of intervals. So if we decrease the number of intervals, so instead of 0 to 1, we can put here 0 from 0, 0.2, 0.4, 0.6, 0.7, 0.8, 8, then 1. Then let's just plot this one. We use our calcu, 0.2, so calc 0.2 equals negative 0.26 or 0.4 0.4 equals, it's negative 0.236. Then next for 0.6, 0.6 equals, it's negative 0.084, negative 0.084. Then for 0.8, 0.8 equals 0.212. Then for 1, it's equal to 0.7. Now let's plot this. So for 0 and negative 0.3. So when x equals 0, our y is negative 0.3. So if this is, let's say this is 1 here. So this is 1. 1, 2, so this is 0. We can just make it here, this one will be equal to 1 para exact siya. 0.8, negative 0.8, negative 1, negative 0.6, then negative 0. Wait. This is the y-axis. That's the y-axis. So the maximum value for the y-axis is 0.7 and the minimum is negative 0.3. So we can make it up to negative 0.3. So let's say this is negative 0.3 here. Let's say this is negative 0.3. Then, so when x equals 0, our y is this one. So this is the first point here. Then when x equals 0.2, so if it's 0.2 somewhere here, if this is 0.2 here, 0.2, then the value is negative 0.26, so somewhere here. Let's just approximate this one. It's just approximation. Then 0.4, 0.2, 0.4, this is 0.4, what happens? It's around negative 0.084. So if this is 0.2, then next here is 0.1, so it's around here. Then after that, it's 0.236, somewhere here. Somewhere here, it's close to 0.26. Then 0.6, negative something, 0.08, then 0.8, this is 0.8, then it will be positive somewhere above here. Then at 1, it's 0.7, so somewhere here. So if we draw the graph, so this will be our f of x. F of x, which is equal to x cubed minus 0.3. So the root is somewhere here. So this will be the root. So in finding this root, you can use any methods. You can use linear interpolation, or you can use quadratic interpolation and find the root. So basically, graphical method is not really useful in solving the exact value, but this is very useful in finding the interval of the root of the function. So here, you can obviously look at from the graph that between 0.6 and 0.8, there's a root. So if there's the interval is smaller, then the iteration and the time needed to find the root will be much quicker. We can find it more quicker and more accurate. So if you do it manually, it's not practical to use the graphical method. But if you do it through various applications like our MATLAB, Octave, Excel, you can use Excel or any plotting application. Then from that, you can look at the interval for the root. You can obviously look at the interval of the root. And if you know the interval, where's the root, it's between 0.6 to 0.8. So that is a very good initial guess now. If we go to the next methods, if you want to calculate more accurate values for the root. And that will be our next method. So this is graphical method. So it's a pictorial way of solving the root. It's not accurate. It's just for finding the interval of the root. And also the next one, the incremental search. Actually, we already did this one. Incremental search. Search method. Sometimes this is called, they also call this one the brute force method. This incremental search method, because we start at a certain point, then we want to find the interval of the root by going either up, increasing or decreasing. So you start on 0 or any point you want. If you grab the function, you find it that it's around, it's in the positive axis, then you can increase. That's the disadvantage of incremental, because you don't know where the function is. It's in the x positive or the negative. So you start at 0 for any point, then you increase, incremental. That's why it's called incremental search until the product of the f of x originally and the new will become a negative. It's a negative, then that's the time that that interval will be the where the root is lying, or we can find the root within that interval. So it's a search method, so it can search the interval. The main purpose of incremental search method is the same as the graphical method, but instead of graphing, you're just solving it through and through until you can find a negative product of the functions, just like what we did here. Actually, this is now incremental search. You can use your calculator directly. And to do that, so let's take that example again. And I will show you how to use your calculator. F of x equals x cubed minus 0.3, and it should be equal to 0. So using a calculator, so click here. Let's reset this one. So you click shift mode, just mode. Then here, there's a table, number 7. So find the table. You press 7. Then next is you type now your equation or your function. So here our function is x cubed alpha x cubed minus 0.3. Then after that, you press equals. Then this one, you can leave it blank because we only need the first one, f of x. Then you press equals. So here, where do we start? So we can start at 0. Then where do we end? So incremental search method, you can make it wider, the search. But if you make it wider, then the solution will be, or the table can be more than, it's too tedious. So we already know that the root of that function is around from 1 to 3, 0 to 3, 0 to 1 actually. But if you don't know it's from 0 to 1, you can just enter 5, then this step. So you can also choose 1. then press equals. So from here, you can see now directly that the f of x changes values sign from 0, x equals 0, to x equals 1 directly. So from that, you can conclude that from 0 to 1, there's a root. So this is just like what we did in the graphical method, but we don't need to graph this because we know that if there's a change sign or variation of the sign of the function, then there's a root. So what we do next again is we decrease the length of the increment from 0 to 1. So we do that again. So shift equals. So we start at 0, still at 0. But this time, we know that it's between 0 to 1. Then, instead of 1, we can use 0.1. We decrease that increment. Then you press equals. Then find again, here, where f of x changes sign. So here, negative, 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 then positive. So it's between 0.6 and 0.7. So that's good. So our new interval now will be 0.6. So x1, 0.6, x2, 0.7. So the root is between them. So if we need more accurate value, then we decrease again the increment. So let's do that again. Equals. So we start, instead of 0, we start at 0.6. Then we end up at 0.7. Then what will be the increment? It's not 0.1 anymore. It should be, we can use 0. It depends on how many significant figure or decimal points you want to be more accurate for your roots. When you 0.01, then you press equals, then find it again here. Negative, negative, negative here. So it's between now 0.66 and 0.67. So it's between 0.66 and 0.67. So if you want a single digit decimal place, now you can just say that the root of this one is 0.7. If you want up to 2 decimal places, then you can do it again, 0.66 and 0.67. You can decrease that again. So this 0.66, 0.67, we can decrease it up to 0.001 and press equals. Then, where is it? There is it. From 0.669 to 0.67. So here, if it's around 0.669 and 0.67. So if the problem says that find the root of this one through incremental search method in 2 decimal places, then you can now answer 0.67. 0.67 is now a good answer. It's accurate up to 2 decimal places. But if you want more decimal places, then you decrease again the incremental. So how about if we try to solve it here directly? Because this is a simple problem, you can solve it directly. And let's see what's the exact value or the true value of this one. So it should be the cube root of 0.3. So what's the cube root of 0.3? Cube root of 0.3 equals. So the true value is 0.66943. So if you look at our answer here, if you use 2 decimal places, your answer is 0.67, then that answer will be a good answer. It's accurate within 2 decimal places. If it's 3 decimal places, 0.669 is also an accurate answer. So conclusion, incremental search method can be used to determine the root or the interval of the root, but the problem with this one is you need to do it, it's more iteration because you don't know where the exact root is. So you do it, you either do it with a wider range for the x, but the problem with the wider range is wider solution. If you can miss also, if you decrease the range, then sometimes you can miss the interval where the solution or the root is lying. So that's the disadvantage. That's why incremental search method, this is only used to determine the initial values, guesses for our roots, so that we use them to in other methods, the next method, the bisection and the false position. So in bisection method, we need to specify the intervals. Where do we start? So how do we start? How do we choose our initial guesses? Then your knowledge from graphical and incremental search will be very, very helpful because it will save you more time in solving the root. So this is the first part, graphical method and incremental search. So the next video will be about bisection, and I will try to incorporate also the last type for the bracketing method, under bracketing, the false position. So next video we will be discussing about bisection method and false position.